So for today's lesson, we're going to learn improper integration. Now this is important. It's important to know this now because in next lesson we're going to learn hydrostatic force problems, and they often use these improper integrals that we're going to talk about to solve them. So it's good to get the basics down now. So the first thing to know about these is you can never have an infinity sign in your integral. You can't have 1 going to infinity. You can't have negative infinity going to some constant. And then you can't have negative infinity passing through 0 and going to positive infinity. It just doesn't work. It breaks math. But we can fix math. And this is called an infinite improper integral. And this integration is kind of special. So we see here, our first example, we have some constant, in this case 1, goes to infinity. Now that breaks math, but we can fix it by substituting this, by substituting that infinity sign. And we substitute it with some other constant. In this case, we'll use b. So the limit because we're going to replace this, so b approaches infinity, is, then our integration, that same constant, 1 to b. That's it. We fixed it. And all that this says is that the limit as some constant approaches infinity, isn't infinity, but approaches it, then we can do the integration. So here we have a negative infinity goes to some constant number. We do this the same way. Limit as b approaches, now in this case it's going to be negative infinity, and then we just replace negative infinity for b. And the constant remains the same. Now this last example, it's a little bit different. It's a negative infinity going all the way to positive infinity, passing through 0 and going all the way to positive infinity. We can't tackle it the same way because there's no constant there. So what we can do is we can break the integral in half and set up some constant. It's suggested that you always use 0, it just makes life easier. We can break it up and put that 0 as our midpoint, or as some point along the way. And what that's going to give us is the limit as b, right, which is just some constant, approaches, and then we're going to use either infinity or negative infinity. In this case, I'm going to start with negative infinity. Negative infinity, the integration sign, so we replace that with b, goes to 0, right? That's just our midpoint, the constant that we chose. And then, because we cut the problem together, so now we have to add the 2 halves back, we're going to add the limit as b approaches positive infinity. And as here it was our top limit, we're going to put it as our bottom. And so we'll just take the last one, the infinity, and we'll put it as b. There we go, guys, we did it.
Okay, the next step in the process with these improper integrals is the same as any other integral. You're going to integrate the integral. So, for instance, if we integrated an integral and found that after integration the function is 1 over x squared, and we're evaluating it 1 to b, this is where it changes. You will not plug in infinity back in for b, you will just treat b as an increasingly large number as we evaluate it. So, all you would do is you would plug in 1 over b squared minus 1 over 1 squared. So b is an increasingly large number. So, with that being in the denominator, that part of the function approaches 0. And subtracting 1 from it does nothing because this number is getting continually larger. This function is going to approach 0. So this function is convergent and converges on 0. Now if we look at one that is a divergent function, so we evaluated or integrated this function and we found it to be, after integration, 2x, and we're going to evaluate it from 1 to b. So you're going to do 2 times b, and b is still an infinitely large number, minus 2 times 1. So 2 times an infinitely large number is approaching infinity, and you're only subtracting 2 from it, so that number, the function is going to get infinitely larger. So it is divergent because it does not approach a number.
So for the examples that we just gave you, we're going to work out an actual example as for solving the integral as the function approaches infinity. So what we're going to do first is we're going to take this infinity and we're going to put a variable to make it go to infinity. So I'll use the variable b as it approaches infinity, and I'll replace it up here as we said before, and I'll leave this constant right here. And I'll write my equation inside of the antiderivative to show that we're going to solve for that. Now, from this point, I can use your class 6 situation of u substitution. So I'm going to take this part of the equation right here, and I'm going to make it my u. Then find the derivative of that. And place this half, which is basically 1 du over 2, in front of my antiderivative, and work it out as a normal u substitution problem. And just to make the situation a little easier, I'm going to take my denominator of u to the third and make it a numerator and just make my exponent negative. Now I can just go ahead and plug in what I had defined as u above over here and continue with my equation. So now that I've done the integration and found out what my problem is after it's been integrated, I can go ahead and plug in my b and my 1 to find out if it converges or if it diverges. So I'm going to start with my b because that's my final product. And this turns into a plus because minus minus makes plus. Now, since b represents infinity, and infinity is on the denominator, this whole function right here is going to go to 0. So we're going to go ahead and factor out this negative 1/4 here just to make the situation easier for us. So it goes right here. And after we plugged everything in, this went to 0, this went to negative 1/9. And essentially, this turns into 1 over 36, which is a value, so a neutral value that doesn't go to infinity or negative infinity. So we can actually say that this problem converges.